Agentic Era explores how Google DeepMind is advancing the frontiers of science with the introduction of Aletheia. This system represents a significant shift toward autonomous mathematics research by utilizing end-to-end natural language processing. Aletheia marks a transition in capability, moving from solving competition-level international mathematical Olympiad problems to tackling complex PhD-level challenges. Unlike previous models, it focuses on autonomous novelty and discovery rather than just verifying existing theorems. This development suggests that AI agents are beginning to participate in the actual creation of new mathematical knowledge. By bridging the gap between classroom exercises and professional research, Aletheia sets a new standard for intelligent agents in highly specialized domains. The current landscape of AI mathematics is defined by the mastery of competition-level problem-solving, often referred to as the gold medal standard. While recent systems have successfully achieved IMO gold performance, these tasks are typically restricted to self-contained problems and the standard high school curriculum. The true challenge lies in the transition to professional-grade research, which demands a more expansive set of capabilities. Research requires the ability to synthesize advanced techniques from vast, unstructured literature rather than working within a closed logical system. Such problems are characterized by long-horizon proofs that often depend on decades of academic context and specialized terminology. Moving beyond competition math means these agents must navigate open-ended environments where the steps to a solution are not clearly predefined. This shift is critical for developing AI that can contribute meaningfully to the global body of mathematical knowledge. Foundation models encounter a hallucination barrier when dealing with specialized domains due to data scarcity. This often manifests as the generation of spurious citations with fictitious authors and titles. In one sample interaction regarding the smooth concordance group of a pretzel knot, the model fabricated a citation to authors such as Livingston and Rasmussen. Another case involving integer divisors showed a reference to a non-existent 1976 paper by Galambos. These fabricated elements are deceptive because extended thinking traces can act as misleading context. This process creates an illusion of logical consistency that inflates confidence in erroneous solutions. Overcoming this barrier is essential for developing trustworthy agents for mathematical research. Aletheia is introduced as an end-to-end natural language research agent designed to solve advanced problems. The system is powered by an advanced version of Gemini Deep Think, which provides the foundation for its deep reasoning. A central innovation of Aletheia is its implementation of a novel inference-time scaling law that enhances its logical depth. To specifically address the issue of fabrication and hallucinations, the agent features intensive tool integration for navigating mathematical literature. This mechanism allows the model to ground its discoveries in verifiable academic contexts, while maintaining a natural language interface. By combining these architectural features, the system aims to move beyond simple problem-solving towards autonomous discovery. The architecture of Aletheia relies on a verification loop that coordinates three distinct subagents. A central problem first flows to the generator, which produces a candidate solution for evaluation. This solution is then passed to the verifier, which determines the next step based on the solution's quality. If the candidate is correct, the verifier generates the final output. If the solution is critically flawed, the process restarts at the generator. For minor errors, a revisor subagent is tasked with making specific fixes before resubmitting. This orchestration implements decoupled reasoning by separating the final answer from intermediate thinking tokens. The system continues this self-correction cycle until a threshold is met or a solution is approved. The engine driving Aletheia's research capability is based on a January 2026 version of Gemini Deep Think. This model is specifically engineered to solve exceptionally difficult reasoning tasks without relying on internet access. A key feature of the engine is its ability to flexibly adjust inference-time compute depending on the complexity of the problem. This allows the system to engage in parallel exploration by testing multiple mathematical ideas simultaneously. By scaling its thinking process, the model can navigate through diverse logical pathways before arriving at a final proof. This mechanism is critical for addressing problems where a single line of reasoning may be insufficient. The advanced engine serves as a robust foundation for the system's high-level autonomous capabilities. To address the critical issue of fabrication, Aletheia utilizes intensive tool integration that incorporates Google search and web browsing. This mechanism allows the model to navigate complex and open-ended mathematical literature as part of its research process. By cross-referencing external databases, the system can verify existing research and identify relevant mathematical sources. This approach effectively cures the problem of citation hallucinations, such as the creation of fictitious titles and authors. This seamless integration transforms the system from a closed generator into a dynamic and verifiable research assistant. It ensures that the model's logic is grounded in established academic foundations while exploring new mathematical territories. Consequently, the reliability of the resulting proof outlines is significantly increased through this real-time verification process. A major breakthrough in Aletheia's development is the 100-fold reduction in compute requirements between successive model versions. The January 2026 advanced version of Gemini Deep Think demonstrates this massive efficiency leap over the July 2025 release. This improvement means that the model can achieve the same IMO-ProofBench performance while utilizing only a fraction of the inference-time resources. Such a reduction is critical for moving beyond competition benchmarks towards scalable and autonomous mathematics research. By optimizing the cost of high-level reasoning, the system becomes more practical for solving complex, multi-step theorems. This efficiency gain suggests that the underlying scaling laws for mathematical reasoning are maturing rapidly. The advanced model now serves as a more accessible platform for intensive, long-horizon mathematical discovery. Aletheia achieves a state-of-the-art accuracy of 95.1% on the Olympiad-level IMO-ProofBench Advanced. This performance significantly outperforms the base Gemini Deep Think model across all tested compute scales, as shown in the benchmark data. When the system selects the problems it chooses to answer, its conditional accuracy rises even higher to 98.3%. These results have been verified by human expert graders to ensure the correctness of each proof. The log-scale analysis of inference-time compute shows that Aletheia provides a substantial performance boost over previous iterations. This success suggests that competition-level mathematics is nearing full automation with current reasoning agents. The gap between the July 2025 and January 2026 versions highlights the rapid pace of development in this field. Transitioning to PhD-level exercises, Aletheia was evaluated on the Future Math Basic internal benchmark. The results show that inference-time scaling laws can successfully transfer to more advanced and research-grade problems. On the subset of exercises the system chose to answer, it achieved a high conditional accuracy of 82%. This level of performance is significantly higher than that of standard inference methods, as indicated by the log-scale compute analysis. These findings demonstrate the critical advantage that the verification mechanism provides in handling graduate-level abstraction. While the performance curves for these complex tasks are more irregular than those at the Olympiad level, the overall trend remains positive. This suggests that the system's reasoning capabilities are beginning to reach the frontiers of academic mathematics. The research team has identified 4 key milestones that define the current era of AI-assisted mathematical work. Milestone A focuses on reliable autonomous research within the field of arithmetic geometry. Milestone B explores AI-guided collaboration involving complex systems of interacting particles. Milestone C introduces semi-autonomous evaluation applied to the vast database of Erdos conjectures. Finally, Milestone D investigates the discovery of new algorithmic bounds for robust Markov decision processes. These diverse applications demonstrate how Aletheia can contribute at various levels of the research process, from independent discovery to strategic planning. Together, these achievements map out a future where AI becomes an essential partner in the advancement of theoretical science. Each milestone provides empirical evidence of the system's ability to tackle problems that have historically required high-level human expertise. Milestone A represents a landmark achievement in reliable autonomous research within the field of arithmetic geometry. The system was tasked with investigating eigenweights for arithmetic Hirzebruch proportionality, leading to the FANG-26 paper. Notably, Aletheia achieved this result with zero human intervention, resolving several questions that were left open in previous academic literature. The AI discovered an elegant solution by utilizing techniques from algebraic combinatorics that were entirely unfamiliar to the human researchers involved. This breakthrough demonstrates the reliability and trustworthiness of natural language models for generating novel mathematical content. It highlights the potential for AI agents to independently pioneer new directions rather than just following human instructions. This level of autonomy marks a significant evolution in the development of intelligent research assistants. Documented logs of the FANG-26 project provide evidence of Aletheia's high degree of autonomy in solving complex group theory problems. The role of human researchers was limited to providing high-level queries and managing paper formatting. When queried on eigenweights for groups of type A, C, and D, the system returned fully correct solutions by synthesizing various advanced tools. These included Aletheia-bot localization, Shor polynomial manipulation, and the Murnaghan-Nakayama rule. The agent also successfully applied Frobenius character identities to provide accurate results across different group variants. This demonstrates that the entire technical core of the proof was autonomously generated by the model. The transparency of this achievement is maintained through the public availability of all raw prompts and outputs. Such evidence establishes a new baseline for the involvement of AI in professional-grade mathematical research. Milestone B focuses on AI-guided collaboration through the investigation of lower bounds for multivariate independence polynomials. In this instance, the traditional research workflow was reversed by using Aletheia as the primary strategist for the project. The problem involved systems where different types of molecules interact without any repelling effects. Aletheia provided the high-level roadmap and the overall strategy for the proof, suggesting the use of specific dual sets. Human mathematicians then performed the rigorous execution based on the inspiration and direction provided by the AI agent. This partnership illustrates how AI can contribute substantive ideas that go beyond simple computation or verification. By serving as a lead strategist, the system demonstrates the ability to manage the conceptual framing of complex problems. This model of human-AI collaboration points to a future where both parties contribute essential insights. The collaboration for the LeCO26 paper illustrates a roadmap where Aletheia manages the logical framework for complex proofs. After Gemini Deep Think solved an initial generalization regarding multivariate inequalities, human researchers queried a more challenging extension. Aletheia responded by generating a detailed proof outline for semi-proper colorings, including several key lemmas. This outline introduced crucial conceptual ideas such as the use of dual sets and the property of log convexity. The agent also applied reduction techniques that helped human mathematicians simplify the remaining proof steps. By managing the high-level logic, the system allowed the humans to focus on refining the final details and devising new proofs. This level of interaction shows how AI can provide both structural and creative guidance in research. All raw prompts and outputs are available to provide full transparency into this collaborative process. Milestone C involves the systematic analysis of 700 open problems from the Bloom database of Erdos conjectures. Aletheia's informal verifier was autonomously deployed to streamline this large-scale candidate pool into a more manageable set. Through this process, the system identified 212 promising responses that warranted further investigation. This semi-autonomous evaluation significantly accelerated the initial screening phase of the research. Each of the identified responses was subsequently vetted by a dedicated team of human domain experts and external auditors. This project demonstrates how AI can serve as a powerful filtering tool for managing vast collections of unsolved mathematical conjectures. The scale of this systematic analysis highlights the model's utility in handling high-volume theoretical research tasks. The analysis of the Erdos conjectures yielded 63 technically correct solutions and 4 autonomous novelty resolutions, including Erdos 652 and Erdos 1051. Among these, 13 solutions were classified as meaningfully correct for successfully capturing the original author's true intent. This effort resulted in the collaborative BKKZ26 research paper, illustrating the productive partnership between humans and Aletheia. In one interaction for the paper, the system provided a correct solution to Erdos 1051, after being queried on its specific summation case. The AI then proposed and refined a meaningful generalization of the theorem, following human requests for deeper insight. This iterative process allowed the team to finalize a rigorous proof and identify optimal examples. The transparency of these results is maintained through the public availability of all raw prompts and outputs. Such successes highlight how AI can move from basic problem-solving to assisting in original theoretical discovery. Milestone D presents a significant achievement in computer science through the discovery of optimal algorithmic bounds for robust Markov decision processes. While human experts had previously derived a valid complexity bound using Siegel's lemma, Aletheia sought an alternative approach. The system devised an independent argument that resulted in the ACGKM26 paper. This new proof achieved the sharpest and most optimal bound currently known among all human and autonomous attempts. Such a result demonstrates that AI is beginning to reach beyond established human limits in theoretical optimization. By finding superior bounds for strongly polynomial policy iterations, Aletheia shows its capability as an independent mathematical researcher. This milestone marks a critical point where AI performance in theoretical work meets and potentially exceeds elite human standards. The rapid advancement of AI in mathematics has led to an evaluation gap, creating a crisis for traditional scientific verification. Peer review for frontier mathematics is exceptionally difficult and often requires more than a year to complete. This significant time delay allows hyperbolic misinformation regarding AI-generated discoveries to spread rapidly across social media. Without immediate and rigorous vetting, terms like revolutionary and viral can distort the true capabilities of these systems. There is now a critical need for responsible documentation and more transparent communication within the research community. Such practices are necessary to differentiate genuine breakthroughs from superficial successes. Addressing this gap is essential for maintaining the integrity of mathematical research in an age of autonomous agents. To address the verification crisis, the researchers have proposed a new taxonomy for defining AI autonomy in mathematical research. This three-tiered framework categorizes contributions based on the level of AI involvement in generating content. The bottom tier represents work that is primarily human, where AI input is minor or auxiliary to the core discovery. The middle tier encompasses substantive human-AI collaboration where both parties make essential contributions. At the top of the pyramid is the essentially autonomous level, where core mathematical content is fully generated by the AI without human intervention. This standardized taxonomy provides a clear language for discussing the evolving relationship between mathematicians and intelligent systems. By clearly defining these roles, the community can more accurately attribute credit and identify current technological limits. Adopting this framework is a critical step toward ensuring transparency in AI-driven breakthroughs. Complementing the taxonomy of autonomy, the researchers have established 5 levels to measure the significance of AI-generated discoveries. Level 0 represents negligible novelty, covering problems like IRDA 652 that have minimal scientific impact. Level 1 identifies minor novelty, exemplified by the solution for IRDA 1051. At Level 2, the AI achieves publishable research grade, as seen in the recent work on eigenweights and independence polynomials. The highest classifications, Level 3 and Level 4, are reserved for major advances and landmark breakthroughs that would traditionally appear in the top 5 global journals. This scale allows the field to track the progression of AI systems as they approach and potentially exceed human performance. Currently, systems like Aletheia are consistently operating within the middle of the significance hierarchy. Standardizing these levels provides a rigorous framework for evaluating the future impact of autonomous mathematical research. To ensure research transparency, the team proposes the Human-AI Interaction Card, or HI card, as an open standard for documenting AI contributions in published papers. This initiative is inspired by model cards in machine learning and requires researchers to expose the raw prompts and outputs containing essential AI insights. The proposed template includes sections for the AI model and version, prompt strategy, and interaction type, alongside human contributions and key insights. By providing a clear record of the system's role in a discovery, the card ensures accountability and precise attribution in mathematical work. This framework addresses the growing need for rigorous documentation as autonomous agents become more integrated into the research process. Standardizing this level of detail is a necessary step for maintaining trust and scientific integrity. The HI card serves as a comprehensive blueprint for researchers navigating this new collaborative landscape. Aletheia represents a divergent intelligence characterized by superhuman breadth rather than the deep, specialized intuition of human researchers. While human mathematicians often focus on narrow areas of expertise, the AI can synthesize knowledge across an expansive array of domains. This breadth allows the system to identify connections that may be obscured by the traditional specialization of human academics. Furthermore, the agent is not constrained by physical limitations, such as time, fatigue, or the finite attention spans of human researchers. This capability suggests that many unresolved conjectures may lie within reach, having been bottlenecked only by human obscurity. By exploring the vast network of mathematical possibilities simultaneously, AI could rapidly accelerate the rate of discovery. This transition from deep intuition to expansive synthesis defines the new potential of autonomous mathematical research. The research by Google DeepMind suggests that the role of AI in mathematics will be as a powerful enhancing tool rather than a replacement for human mathematicians. This future depends on the successful integration of autonomous agents like Aletheia into the professional workflow. By taking on the role of strategist or independent investigator, these systems allow human researchers to focus on higher-level conceptual questions. The team has committed to transparency by providing an open-source repository of all raw prompts and model outputs. This database allows the global community to verify the system's achievements and refine its future contributions. Moving forward, the focus will remain on developing these systems as reliable partners for theoretical discovery. This partnership aims to expand the current boundaries of mathematical knowledge through the combination of human depth and AI breadth.